Welcome to Axor Galactic Observatory, where Rigel in Orion reveals the violent future awaiting massive stars. Across Orion's winter geometry, Rigel burns like certainty, while distance hides the instability beneath that brilliance. Rigel seems a familiar beacon, yet its calm glow already belongs to a star under strain. Its brightness feels triumphant, but extreme luminosity spends order recklessly and converts splendor into shortened time. That blue-white glow spreads through Orion like cold fire, warning that beauty here means danger. Rigel's color records furious heat, immense radiation, and a rate of burning no giant sustains long. Mass gives Rigel enormous power, yet that same power hastens its death and starts the countdown. Beneath the light gravity and fusion bargain uneasily within a core that cannot negotiate forever. Inside that hidden furnace pressure rises with every triumph, because success in massive stars carries ruin. Rigel does not merely possess fuel, it destroys that fuel so fast, abundance becomes brevity. Its blue supergiant expansion looks majestic, yet swollen layers signal a star drifting away from equilibrium. Radiation drives stellar winds outward, stripping matter away and proving luminous stars are difficult to hold. Rigel is not fully alone. Orion hides a broader system and a more layered history. The wider environment deepens the story as neighboring gravities turn one bright landmark into context. Fusion does not stay simple because heavier burning stages form harsher interiors and narrower futures. Iron finally ends the bargain because fusion yields no rescue there and gravity stops waiting. After millions of years, the decisive collapse arrives in moments when the core abruptly gives way. The supernova releases buried energy and forged elements outward, but the explosion is not everything. Neutron star or black hole, Rigel's ruin becomes inheritance, seeding later stars, planets and worlds. After Rigel, Orion stops being familiar and becomes a living lesson in cosmic impermanence tonight. Like, subscribe, and thank you for listening. Now follow Rigel from familiar beacon toward hidden danger. Rigel looks eternal only because human eyes are small. What hangs in Orion as a clean blue-white point feels fixed, decorative, almost ceremonial, a winter star that seems to exist for orientation and nothing more. But the surface impression is misleading from the first second, because Rigel is not important for being visible. It is important because it is unstable at a scale that makes ordinary stellar language sound timid. The familiar story says that Rigel is simply one of the brightest stars in the night sky. The real story is that it is a massive star already living inside the logic of catastrophe, a star so luminous, so energetic, and so structurally expensive that even its calm appearance is part of the deception. This only looks peaceful from about 860 light-years away. Distance smooths violence. Distance turns a stellar crisis into a jewel. Distance hides the fact that Rigel is not just shining, but spending itself with extraordinary aggression. To see the deeper story, it helps to begin not with poetry, but with scale. The Sun dominates the solar system so completely that Earth, every planet, every asteroid, every comet, and every trace of drifting debris amount to a thin afterthought beside it. Yet Rigel stands far beyond the Sun in luminosity and size, radiating tens of thousands of times more energy. It is hotter at the surface, more massive than the star that makes life on Earth possible, and less secure because of that power. Here the first contradiction appears. In everyday thinking, greater size suggests greater durability. Large things feel harder to break. Mountains outlast houses. Oceans outlast storms. Stars do not obey that intuition. In stars, more mass means more pressure in the core. More pressure means faster fusion. Faster fusion means more light. And more light means the star begins paying its future away at a terrifying rate. The achievement is real. The cost is larger. Rigel is not a monument to stellar stability. It is a demonstration of how quickly nature can burn through greatness when enough fuel is compressed into one place. That is why the obvious explanation is not the real one. Rigel is not extraordinary merely because it is big. It is extraordinary because it is burning under conditions that make bigness dangerous. The blue color matters here. To human perception, blue-white stars can look pure, clean, almost cold in their clarity, but in stellar physics, blue is not restraint. Blue is heat. Blue is pressure made visible. Blue is the signature of a surface so hot that the star pours energy into space with a violence the sun never approaches. Rigel's light, therefore, is not just illumination, it is evidence. It tells us that the outer layers are being driven by a ferocious engine below one, built on the temporary balance between inward gravity and outward pressure from fusion. That balance sounds stable when stated abstractly. It is not stable in the ordinary sense. It is a negotiated truce inside an object that would gladly collapse if fusion weakened. A star is not a lamp. A star is a controlled failure of collapse. In modest stars, that failure can be maintained for billions of years. In massive stars like Rigel, the same arrangement becomes much harder to keep under control because the numbers stop being forgiving. Gravity squeezes harder, temperature rises, fusion accelerates, radiation intensifies. The whole system becomes more brilliant and more wasteful at the same time. This is why the story on the surface is smaller than the story underneath. What the eye sees is a bright star in Orion. What physics sees is a machine devouring its central reserves at a rate that makes stellar longevity impossible. That matters because human beings instinctively imagine the sky as a backdrop. Constellations look arranged. Seasonal stars return. Orion rises and sets with such reliability that it encourages a false kind of trust. Rigel participates in that illusion. It helps create one of the most recognizable patterns in the heavens, and because the pattern persists across generations, the mind quietly assumes the objects inside it are equally settled. They are not. Constellations are visual habits, not physical communities. Rigel's story is not the story of a placid marker pinned to the night. It is the story of a massive star already far along a path that only ends one way. Not tomorrow, not on any human schedule, but within the logic of stars with startling speed. This is the point where the deeper question finally emerges. What exactly is a massive star buying with all this brilliance, and why does the purchase always end in ruin? The answer begins with a fact that is easy to say and hard to feel. Stars live by resisting their own weight. Gravity constantly tries to force matter inward. Fusion in the core pushes back outward. As long as those two powers remain in balance, the star survives. But balance is not peace. Balance is expenditure. A star remains itself only by burning fuel, and a massive star remains itself only by burning fuel extravagantly. Rigel, therefore, is not simply existing. It is defending its form every second through an immense release of energy. The brighter the defense, the shorter the defense can last. That is the real significance of Rigel at the beginning of this story. It is not just a beautiful star. It is a warning written in blue light. It shows that in the upper ranks of stellar mass, splendor and fragility are not opposites, but partners. The very traits that make such stars dominant across interstellar distances also ensure that they cannot remain what they are for long. And once that truth becomes visible, the next layer becomes unavoidable, because the question is no longer why Rigel is bright. The question is what a star must do internally to shine like this at all, and what kind of price a core must be paying to keep that light alive. Brightness feels like a simple virtue until you ask what it costs to sustain. From Earth, Rigel seems to prove that brilliance is a kind of triumph, a star so conspicuous that it holds its place in Orion with the confidence of an object built to endure. But luminosity is not a trophy a massive star wins after achieving greatness. It is a bill the star must keep paying every second it remains itself. The obvious explanation is that Rigel shines so fiercely because it is large. The real explanation is harsher. Rigel is bright because its core is under such immense pressure that it must generate energy at a staggering rate just to avoid collapse. And that requirement turns light into evidence of strain. In ordinary life, power suggests security. In stars, power often signals the opposite. The more massive the star, the harder gravity presses inward. The harder gravity presses inward, the hotter and denser the core becomes. The hotter and denser the core becomes, the faster nuclear fusion must proceed to push back. That chain is the hidden architecture of Rigel's brightness. It is not glowing generously. It is resisting destruction at colossal speed. This is why massive stars live such short lives compared with stars like the Sun. They possess a larger reservoir of fuel, but they burn through that fuel vastly faster because the terms of the balance are so much more severe. The achievement is real. The waste is enormous. Rigel therefore belongs to one of the most revealing categories in astrophysics objects that look abundant from the outside while racing toward exhaustion from within. That contradiction is difficult for human intuition to accept because vision misleads us. When people look at a bright star, they instinctively imagine permanence. The sky teaches the wrong lesson by repetition. If something returns winter after winter, generation after generation, the mind begins to file it under reliable. Yet a star can be visually dependable on human timescales and existentially precarious on stellar ones. Rigel is a perfect example. It is young by the standards of ordinary stars only millions of years into its existence, not because youth guarantees safety, but because massive stars simply do not get much time. They burn too intensely for that. A smaller star can live quietly for billions or even trillions of years, stretching its hydrogen budget with relative discipline. A giant blue star cannot. It burns like a civilization spending tomorrow's inheritance to dominate today. This is the deeper meaning of luminosity. To say that Rigel is tens of thousands of times more luminous than the Sun is not just to compare levels of brightness. It is to describe the rate at which the star is converting its internal order into outward radiation flooding space with the product of a core working under extraordinary demands. The star looks rich because it is spending itself lavishly. The story on the surface is abundance. The story underneath is accelerated consumption, and distance makes this easy to miss. Rigel is far enough away that what arrives here is only the finished light detached from the mechanism that produced it. We do not see the compression in the core. We do not see the flow of energy forcing its way outward through dense stellar layers. We do not see the long-term structural cost of radiating so much power. We see a point of light. Astronomy begins when that visual simplicity is refused. Rigel is not just bright in appearance. Its intrinsic luminosity is immense, which means even after accounting for distance, the star itself is truly extraordinary. That distinction matters because apparent brightness can flatter. A nearby modest star can look noticeable, while a distant giant can be hidden by sheer remoteness. Rigel escapes that confusion because it is both prominent to the eye and intrinsically immense, one of the great luminous markers of the nearby sky. But prominence is not the final truth. It is the clue. The larger truth is that luminosity on this scale changes the entire life strategy of the star. Instead of easing through the long central chapter that defines more modest stars, Rigel is forced into an expensive mode of existence from early on. Its core pressure is greater, its fuel consumption is faster, its evolutionary path is steeper. Everything important happens sooner. This is what makes the star dramatic even before any explosion enters the story. Catastrophe does not begin at the end. It begins in the conditions that make the end inevitable. Rigel's brilliance is one of those conditions. The star is already telling us what kind of future it belongs to, because stars this luminous do not fade into quiet retirement. They move toward deeper instability, stronger winds, more violent internal transitions, and finally collapse. The light is not separate from that outcome. It points toward it. A star cannot shine at this level without changing its own future. And the closer one looks, the more the brightness itself becomes unsettling. It means the surface is fed by a furnace far more intense than the sun's. It means the outer layers are being held up by a flow of energy that must remain immense simply to keep gravity from winning. It means the star is not coasting, it is fighting. This is the point where admiration should turn into suspicion, because what appears majestic is also revealing a kind of built-in urgency. Rigel is not bright because it is comfortable. Rigel is bright because it is under pressure. And once that becomes clear, the next question changes as well. The issue is no longer how brilliant the star looks in Orion. The issue is what kind of temperature radiation and physical violence must exist at the surface of a star whose light carries this much force into space, and why blue starlight is really the visible edge of a far more dangerous reality. Blue is one of the most misleading colors in the universe. To human instinct, blue often suggests calm distance clarity, even coolness, as if the star at Orion's foot is somehow cleaner and more composed than the warmer orange and red lights scattered elsewhere across the sky. But stellar color obeys a harsher logic. In stars, blue does not mean gentle. Blue means hotter. Blue means the surface has been driven to such extreme temperatures that the star radiates with a violence far beyond the sun. And this is where Rigel's appearance stops being decorative and starts becoming diagnostic. Its blue-white light is not a cosmetic trait. It is physical testimony. It tells us that the outer layers of the star are blisteringly hot, that energy is surging outward at a staggering rate, and that the star is living under conditions no massive object can maintain for long. The obvious explanation is that color is just what we happen to see. The real explanation is that color reveals the state of the engine. A star's surface temperature shapes the light it emits, and hotter stars push more of that light toward the blue and ultraviolet part of the spectrum. That shift matters because ultraviolet radiation is not a minor adjustment in style. It is a sign that the star is shedding energy with ferocious intensity. Rigel therefore does not merely outshine many stars in visible light. It also floods its surroundings with radiation. The human eye cannot even register directly, which makes its apparent beauty only the narrow visible edge of a much larger physical assault on space. This only looks elegant from far away. Up close, a star like Rigel is not serene at all. It is an immense radiating surface so hot that ordinary planetary life could never negotiate with it, orbit near it, or treat it as a stable long-term source of comfort. The Sun, for all its dominance over Earth, is moderate by comparison. Its surface is hot enough to sustain a living world at the right distance. But Rigel belongs to a far more extreme category where radiation becomes not just a source of light, but a structural force. That force matters because radiation does not simply leave the star and vanish into the dark. It pushes, it transfers momentum, it presses against the star's own outer layers. In massive stars, this outward pressure becomes so strong that the star begins to lose matter through stellar winds, sometimes on enormous scales. So the color is already doing two jobs at once. It tells us how hot the surface is, and it hints that the star's own brightness is beginning to undermine its ability to remain whole. This is the deeper tension inside blue starlight. Greater temperature means greater power, but greater power means greater instability. The achievement is real. The self-damage is real too. Human beings are used to thinking of heat as a local property. A fire burns here. A furnace glows there. A hot object can be approached, measured, managed. Rigel destroys that intuition because its heat is inseparable from scale. This is not a hot rock or a hot atmosphere. This is a stellar surface of enormous size, radiating at temperatures that transform the meaning of exposure itself. If a planet orbited at a distance that gave it the same sunlight Earth receives from the Sun, that world would need to be placed astonishingly far away. And even then, the problem would not be solved cleanly because the character of Rigel's radiation is different. A star this hot does not merely provide illumination. It sculpts its environment through intense ultraviolet output, ionizing nearby gas, driving energetic processes through the surrounding medium, and announcing that extreme stars do not simply sit inside space. They reorganize it. This is why the surface story keeps collapsing into a larger one. Rigel first appears to be a single bright star. Then, it becomes a massive blue supergiant. Then that supergiant becomes a radiation source, powerful enough to reshape matter beyond itself. The object keeps widening into a system of consequences. And yet, even that is not the deepest layer, because the blue-white surface is not the cause of the violence. It is the symptom. The real problem is not what the surface is doing. It is what the core must be doing to force the surface into this state at all. Every second, the interior must generate enough energy to support this furious outward flow. Every second, fusion must continue under extreme pressure, feeding the brightness, holding gravity back, and maintaining a structure that becomes more expensive the more brilliant it is. This is why blue massive stars cannot be judged by appearance alone. Their very color tells us they are living quickly. It tells us that they are converting internal fuel into outward force at an extraordinary pace. It tells us that long survival is becoming less likely precisely because the star is so successful at being powerful now. The answer seems clear until the scale becomes visible. Then the meaning changes. Rigel is not blue because it is calm enough to glow beautifully. Rigel is blue because its surface has been driven into a regime of temperature and radiation that only a deeply pressurized, deeply temporary stellar engine can sustain. This is not a color of safety. It is a color of expenditure. And once that becomes clear, the next question stops being about light and starts being about time, because a star can only radiate like this by burning through its future at tremendous speed. Which means the real mystery is no longer how hot Rigel is, but how long any massive star can possibly survive once nature has made it this powerful. The giant stars die first. That sounds wrong on first contact, because almost everything in ordinary experience teaches the opposite lesson. Large trees outlast saplings. Thick walls outlast thin ones. Great reservoirs endure longer than small cups. So when the mind first meets a star like Rigel, it reaches instinctively for the same rule and assumes that greater mass must mean greater staying power. But stars are not preserved by having more substance to spend. They are judged by the rate at which that substance must be spent to resist collapse. And in that accounting, mass is not mercy. Mass is pressure. Pressure is speed. Speed is loss. This is the hidden law beneath the glamour of blue supergiants. The obvious explanation is that a massive star should live longer because it begins with so much more fuel than a star like the Sun. The real explanation is that gravity changes the terms so violently that the larger supply becomes almost irrelevant. Add enough mass to a star, and the core is squeezed harder. Squeeze the core harder, and its temperature rises. Raise the temperature, and nuclear fusion accelerates dramatically. Accelerate fusion, and the star floods space with more energy, shines far more brightly, and burns through its reserves with astonishing wastefulness. The result is one of the most important contradictions in astrophysics. The stars born with the greatest power inherit the shortest lives. They dominate the sky. They do not keep it for long. This is why Rigel matters as more than an isolated object in Orion. It reveals a general truth about the upper world of stars, where greatness and brevity are tied together from the beginning. A modest red dwarf can burn its hydrogen with extraordinary patience, stretching existence across spans so long that they make the present age of the universe feel young. The Sun, heavier and brighter, pays more for its stability and lives on a shorter but still immense timetable of billions of years. Rigel belongs to a different order entirely. Its mass forces it into a regime where abundance becomes liability. The star may begin with far more fuel than the Sun, but it also consumes that fuel at a rate so much greater that the comparison becomes almost cruel. It is like comparing a candle to a furnace and asking which one should last longer, merely because the furnace is larger. Size is not the decisive variable. Consumption is. The achievement is real. The tempo is fatal. This is why the language of stellar evolution becomes unintuitive precisely where the stars become most impressive. Human beings are drawn toward the largest and brightest objects as if they represent completion, the summit of stellar success. But a massive star is not a final form. It is a rushed arrangement. Nature piles vast amounts of matter into one place, and for a brief period, the result looks magnificent. Yet the very conditions that produce the spectacle also guarantee a compressed life. The star spends its youth in a blaze of output that would be impossible for smaller stars and unsustainable for itself over the long term. So when astronomers say that massive stars die young, they are not making a poetic observation. They are describing the direct consequence of physics under extreme compression. Rigel does not age slowly into wisdom. It races through phases of existence that smaller stars take far longer to approach, and it does so because its own weight leaves it no gentle path. Gravity is the real author here. The story on the surface is brightness and scale. The story underneath is the pressure of being too massive to live quietly. That pressure does more than shorten the calendar. It changes the whole structure of the star's future. Massive stars do not simply burn hydrogen and then fade. They are pushed toward deeper and harsher stages of fusion, toward swelling outer layers. violent winds, chemical stratification, and finally collapse. Their lives are not only short, they are crowded. A star like Rigel must pass through evolutionary chapters that become progressively less forgiving, because once the easiest fuel is exhausted, the core contracts further heats further and forces the star into new bargains that grow more expensive each time. In that sense, youth itself becomes deceptive. Rigel is relatively young, but youth here is not a sign of safety. It is evidence of how fast the clock runs when a star is built on such extravagant terms. That is another contradiction worth holding on to. In ordinary thinking, youth suggests time ahead. In massive stars, youth may simply mean the system never had much time to begin with. The answer seems clear until the scale becomes visible. Then the logic reverses. The biggest stars are not long-lived elders of the cosmos. They are brilliant sprinters burning through impossible amounts of order for a brief reign before structural failure closes in. And this changes the emotional meaning of the night sky. Rigel is not just an old beacon that has watched uncounted winters pass over Earth. It is a star in a hurry, one whose very existence is being shaped by the fact that immense mass cannot be held in balance cheaply. The more matter gravity piles into the core, the more severe the counterforce must become. The more severe the counterforce becomes, the more energetically the star must live. And the more energetically it lives, the faster it approaches the moment when the old balance can no longer hold. This is the larger truth hidden inside stellar grandeur. Massive stars die young, not because nature is unfair, but because power at this level is intrinsically expensive. Every extra advantage comes tied to deeper instability. Every increase in mass sharpens the internal demands. Every burst of brightness announces a faster loss of future. Which means the next layer of the story is no longer about lifespan in the abstract. It is about the exact place where that lifespan is negotiated and consumed. Because if Rigel is living quickly, then the real drama is not in its famous light at all, but in the core beneath it, where gravity and fusion are locked together, under pressures so immense that the star's entire fate is being written there. What matters is not the star we see, but the star we do not. Rigel's blue-white surface, its enormous luminosity, its rank among the dominant lights of the winter sky, all of that is real, but none of it is the true center of the story. The real center is buried. It is hidden beneath vast layers of hot gas, far below the light that escapes into space, in a core where gravity and pressure force matter into one of the most violent balances in nature. This is the place that decides everything. The obvious explanation is that a star shines because it is hot. The real explanation is that a star shines because its core is trapped in a continual contest against collapse, and every visible feature on the outside is downstream from the terms of that contest. Rigel is not bright because the surface somehow chooses to glow. Rigel is bright because the core beneath it is under extraordinary compression, and that compression drives fusion hard enough to keep the whole star from falling inward. A star is therefore not a burning object in the ordinary sense. It is a structure being held open by reactions deep inside it. Reactions that exist only because gravity has made the core dense and hot enough to force atomic nuclei together. That simple statement becomes much more dangerous when the star is massive. In a smaller star, the balance between inward gravity and outward pressure can hold for immense spans of time because the core conditions, while extreme by human standards, are still relatively moderate by stellar ones. In Rigel, moderation is gone. The star's great mass bears down on the center with immense force, and the core responds the only way matter can respond under such pressure. It heats, it densifies, it drives fusion faster. This is the deeper mechanism behind everything described so far. The brightness is not the first fact. The pressure is. The color is not the first fact. The compression is. The story on the surface is light. The story underneath is a core being asked to do brutal work without pause. To understand why that matters, it helps to strip away the comforting picture of a star as a smooth, glowing sphere. Rigel is better understood as a layered negotiation. Gravity pushes inward on every part of the star, but the central regions bear the greatest burden because they support all the mass above them. That burden raises temperature and pressure to staggering levels. Under those conditions, hydrogen nuclei move fast enough, collide hard enough, and fuse efficiently enough to release enormous amounts of energy. That energy does not escape instantly. It fights its way outward over long timescales through the star's interior, and in doing so, it provides the outward pressure that keeps the star inflated. So the star's size, temperature, and luminosity are not static qualities. They are the visible consequence of a vast internal traffic of energy born in the core and paid for by fuel. This is why the core is the real seat of destiny. Change the core and the whole star changes. Exhaust the easiest fuel in the core and the structure above it must readjust. Increase the pressure and the reactions accelerate. Disturb the balance and the star begins evolving into something new. The surface can delay this truth. It cannot escape it. And here the contradiction becomes sharper. The core is where the star is strongest, because fusion there allows Rigel to resist its own weight. But the core is also where the star is most vulnerable, because the same fusion that preserves the star steadily transforms the conditions that preservation depends on. Every reaction spends fuel. Every reaction alters composition. Every reaction inches the core toward a future in which hydrogen is less available. The pressure balance changes and contraction begins again in new form. The achievement is real. The instability is built in. This only looks like a stable object from a great distance. In physical reality, Rigel is a temporary agreement between the forces that do not want the same outcome. Gravity always prefers concentration. Fusion-generated pressure holds that concentration back. For a while, the two can coexist in dynamic balance. But they are not allies. They are adversaries locked in a truce that lasts only as long as the core can keep paying the energy cost. That is why the deepest question is never what the star looks like tonight. The deepest question is what fuel remains in the center, what reactions dominate there, and how much longer the core can continue dictating order to the rest of the star. Once that question comes into focus, Rigel stops looking like a bright object and starts looking like a countdown governed from within. The outer layers may swell, shift, or shed matter. The radiation may intensify. The winds may strengthen. But none of those are the primary driver. They are symptoms of the central bargain. The real problem is not on the surface. It is in the compressed interior, where the next phase of the star is always being prepared before the rest of the structure knows it. This is what makes massive stars so dramatic. Their cores are not quiet furnaces. They are accelerating engines. Because gravity is stronger, the temperatures are higher, the fusion is faster, and the margin for a long, uneventful life is much smaller. Rigel lives in that regime. The star's grandeur depends on a core doing immense work every second, and that work cannot continue indefinitely on the same terms. So the hidden truth of Rigel is not merely that it is hot, luminous, or large. It is that the center of the star is a place where matter is being forced to buy stability through extreme expenditure, and every second of successful resistance also reduces the future supply that makes that resistance possible. Which means the next layer of the story is no longer about pressure alone. It is about depletion, because once the core is understood as the engine of the whole star, the unavoidable question becomes how quickly such an engine can consume its fuel before the balance begins to fail. Having more fuel means very little when the engine is built to waste it. That is the next hard truth hidden inside Rigel. After seeing the pressure in the core, it becomes tempting to think the star's great mass still gives it some protective advantage, as if an enormous reserve must surely compensate for the speed of consumption. But this is where ordinary arithmetic fails. Stars do not live or die by total supply alone. They live or die by the ratio between supply and expenditure, and Rigel belongs to a class of stars where expenditure becomes so extravagant that abundance is almost swallowed by it. The obvious explanation is that a massive star lasts a long time because it begins with more hydrogen than the Sun. The real explanation is that the increase in fuel is overwhelmed by the increase in burn rate. Rigel is not merely a bigger lamp with a bigger tank, it is a more aggressive furnace, forced by gravity to process its reserves at a pace that turns stellar life into a brief and violent episode. This is why the phrase "massive stars die young" is not just a summary of the previous section. It is the direct consequence of fuel being consumed under extreme conditions. The Sun has enough hydrogen in its core to sustain a stable main sequence life for about 10 billion years. A star in Rigel's class does not receive that kind of leisurely calendar. Its internal demands are too high. Its core temperatures are too great. Its fusion reactions run too intensely. So even though the star begins life with far more raw material, it chews through the usable part of that material with such ferocity that the total lifespan collapses from billions of years to only millions. This is the deeper insult written into the lives of the most powerful stars. Nature gives them more to spend, then forces them to spend it catastrophically fast. The achievement is real. The inefficiency is staggering. To feel the scale of that difference, it helps to stop thinking in terms of glowing points and start thinking in terms of time. The Sun can afford patience. Its life unfolds across intervals so huge that continents rise and erode, oceans open and close, whole branches of biology appear and vanish, and the star still remains in the long central stability of its existence. Rigel does not inhabit that kind of time. Its life is compressed. Its phases arrive earlier. Its transitions crowd together. It is born into urgency. In human terms, the contrast is almost obscene. If the Sun is a civilization with a deep treasury spending cautiously across ages, Rigel is an empire burning through unimaginable wealth in a campaign too ambitious to sustain. It can dominate the horizon for a while. It cannot make that mode of existence last. This only looks like abundance from the outside. Inside, the star abundance is being converted into pressure into fusion into light, and light into loss. That chain is the true biography of Rigel. Every second, the core converts part of its hydrogen into helium, releasing the energy that keeps the star from collapsing. But the process does not merely reduce the fuel supply. It changes the structure of the core itself. Helium ash builds up. The composition shifts. The easy phase of stellar life begins to narrow. And because the star is so massive, even the early stable chapter proceeds under such intense conditions that the transition toward instability comes much sooner than intuition expects. This is the important reframing. Rigel is not a star with a lot of time left because it has a lot of mass. Rigel is a star with relatively little time left because all that mass has made a slow life impossible. The fuel does not fail because there was too little of it. The fuel fails because the terms of survival are too expensive. In smaller stars, modest pressure allows hydrogen fusion to proceed with restraint, stretching existence into long eras of continuity. In Rigel, the same fundamental physics is driven into a more punishing regime. The star must burn hotter to support itself. It must shine harder to remain inflated. It must release more energy because gravity is asking more of it. And that means every advantage arrives attached to accelerated depletion. This is why high mass is not simply a larger version of low mass. It is a different strategic problem entirely. Add enough matter, and the star is no longer granted the luxury of caution. It becomes trapped in a high-output existence where fuel is consumed not in a slow stellar economy, but in a kind of internal emergency. That emergency can last millions of years, which sounds immense until it is compared with the lives of smaller stars. Then its brevity becomes shocking. The answer seems clear until the scale becomes visible. Yes, Rigel has more to burn. But it is burning so much faster that the surplus behaves less like security and more like the raw material for a brighter collapse. And that alters the meaning of the whole star. Its light is not simply evidence of strength. It is evidence of how fast future time is being destroyed in exchange for present power. This is the hidden cost of stellar magnificence. Massive stars win the contest of brightness by sacrificing the contest of endurance. They become dominant but not durable. They command the sky but not the calendar. And once that becomes clear, another layer opens beneath it, because fuel exhaustion is not just a matter of less hydrogen being available tomorrow. It changes what the core must do next. As hydrogen runs low in the center, gravity begins reclaiming ground. The core contracts. Temperatures rise further. New forms of burning become possible. The star does not simply dim and fade. It is forced into harsher bargains, each one shorter, hotter, and less forgiving than the last. Which means the depletion of fuel is not the end of Rigel's story. It is the mechanism that pushes the star out of stability and into a much more dangerous phase where growth itself becomes suspect, and the star's expanding grandeur starts to hide a deeper structural instability. Growth is not the same as safety. That is the next reversal Rigel forces on the story. By now, the star has already shed the comforting illusion of permanence, but another illusion waits behind it. The idea that a star becomes more secure as it grows into a supergiant, as if greater size means it has settled into some mature and commanding final form. The opposite is closer to the truth. A blue supergiant is not a star that has escaped danger by becoming larger. It is a star whose structure has become more expensive, more delicate, and more dependent on conditions that cannot last. Rigel, a massive blue supergiant in Orion, is often described in terms of grandeur roughly 20 times the Sun's mass, at least 70 times its radius, and vastly more luminous than the Sun. And those numbers are real, but they are easy to misread. The obvious explanation is that expansion signals dominance. The real explanation is that expansion often signals structural trouble. When the core of a massive star changes, the outer star must respond, and that response can make the whole object look grander at exactly the moment its inner stability is becoming harder to maintain. This is one of the most important reframings in stellar evolution. Bigger is not always better organized. Bigger can mean looser control. Bigger can mean the energy generated in the interior is being redistributed through layers that are more distended, less tightly bound, and more vulnerable to radiation-driven loss. In a star like Rigel, the swollen outer envelope is not a symbol of calm completion. It is part of a deeper instability that begins when the easy phase of core burning no longer defines the whole star as cleanly as before. The story on the surface is enlargement. The story underneath is adjustment under pressure. To understand why it helps to remember what a star's size actually means. A star is not a rigid body like a planet or a steel sphere. Its radius is the outcome of a balance between gravity pulling inward and pressure pushing outward. Change the internal conditions and the size can change dramatically. So when a massive star swells into supergiant dimensions, that is not merely a cosmetic increase. It is a declaration that the old balance has shifted. The core has changed. The pressure pattern has changed. The outer layers are being held farther out than before, and that new arrangement comes with costs. Gravity at the surface weakens. The outer gas is bound less tightly. Radiation has more leverage. Mass loss becomes easier. This is why a blue supergiant can be both enormous and precarious at the same time. The achievement is real. The fragility is hidden in the scale. Human beings are naturally impressed by size because size feels like surplus. Yet in stars, surplus can produce weakness. Stretch matter across a larger radius, and the outer layers live farther from the stabilizing grip of the center. They remain part of the star, but less securely than before. In massive, luminous stars, that matters enormously because the outward pressure of radiation is no trivial effect. Blue supergiants are among the most luminous stars known, and Rigel's light output is so extreme that its own radiation helps drive matter away in stellar winds. So the star is not just shining. It is eroding. It is not just existing at great scale. It is paying maintenance on that scale by losing part of itself. This is where the emotional meaning of expansion changes. What first appears as the flowering of stellar power begins to resemble a costly overextension. Rigel grows large, not because nature has granted it peace, but because the internal evolution of a massive star forces the outer layers into a more inflated and less secure configuration. The expanded star can radiate tremendously. It can dominate the sky across huge distances. But the larger structure is also harder to hold together cleanly because the same luminosity that advertises the star's power also pushes against the gas it is trying to retain. This only looks like majestic enlargement from far away. Physically, it is a star living in a regime where size and self-loss begin to support each other. That feedback matters because it means expansion is not a neutral stage. It changes the star's future. As mass is shed, the outer structure evolves further. As the core keeps changing, the envelope must keep responding. The star becomes not a settled object, but a moving compromise between interior necessity and exterior leakage. That is why the phrase blue supergiant should not be heard as a title of triumph. It should be heard as a warning label. It tells you the star is massive enough, luminous enough, and structurally extreme enough that ordinary stellar longevity is already gone, and even its enlarged form is difficult to sustain. Rigel is close enough and bright enough to feel like a fixed part of the sky. Yet its class belongs to a population of stars that live fast and radiate furiously. Britannica describes it as a supergiant about 860 light-years away, and intrinsically one of the brightest stars in the sky, while NASA's glossary notes that blue supergiants like Rigel are among the brightest stars in the universe. Those facts are not decorations. They are clues to the underlying physics. Extreme brightness means extreme output. Extreme output means stronger radiation pressure. Stronger radiation pressure means a greater struggle to keep the outer layers bound. The answer seems clear until the scale becomes visible. Then growth stops looking like reassurance and starts looking like a symptom. Rigel's expanded body is not proof that the star has reached a safe and stable maturity. It is evidence that the easy equilibrium is already being replaced by a more expensive arrangement, one in which the outer layers are puffed outward. The star's grip on its own matter is less secure, and luminosity itself begins to act like a slow instrument of self-destruction. Which means the next layer of the story is not the size of the star at all, but the material streaming away from it. Because once a supergiant begins living under these terms, its light is no longer only making the star visible. It is helping take the star apart. A star can be so bright that its own light begins to unmake it. That is the next threshold in Rigel's story, and it is one of the strangest. By now, the pattern is familiar. Every feature that first looks like advantage turns out to contain a hidden cost. Great mass shortens life. Great brightness signals pressure. Great size hides instability. Now the same reversal reaches the star's outer layers. The obvious explanation is that Rigel shines and space receives the light. The real explanation is that the light does more than travel. It pushes. It transfers force. It helps drive matter away from the star in a continuous outflow called a stellar wind. And in massive blue supergiants, that wind is not a side detail. It is part of the central drama. Rigel is not simply holding itself together while radiating into the dark. It is losing itself while it shines. This only looks like a fixed object from far away. In physical terms, the star is shedding material into space, grain by grain on the human scale, but at enormous rates on the stellar one, because its luminosity is high enough, and its outer layers are loosely bound enough that radiation can help lift gas away from the surface. That changes the emotional meaning of brightness again. Light is no longer just the sign of energy being released. It becomes an instrument of erosion. The achievement is real. The self-loss is real too. To understand why it helps to abandon the image of empty space as passive emptiness. The region around a massive star is not a silent vacuum in which light simply disappears. Radiation interacts with matter. In the hot extended atmospheres of blue, supergiants' atoms and ions can absorb momentum from the star's intense radiation field. That momentum is then transferred to the gas accelerating it outward. The result is a wind, not in the planetary sense of moving air over a surface, but in the stellar sense of a continual stream of particles and gas escaping the star's grip. A smaller, dimmer star like the Sun has a solar wind, but in stars like Rigel, the scale, energy, and consequence are much greater. The outer layers are already less securely bound because the star is so large and the luminosity is so extreme that the star's own radiative output becomes a kind of pressure system working against retention. So when Rigel shines, it does not merely reveal its existence. It participates in changing its own mass. That matters because mass is not decorative. Mass governs the future of the star. Strip enough of it away and you change how the star evolves, how its core and envelope interact, how later phases unfold, and what kind of death eventually becomes possible. The story on the surface is a bright blue supergiant in Orion. The story underneath is an object already negotiating with loss. This is one of the reasons massive stars are so difficult to describe honestly in static terms. Human language wants a clean noun, a star, a giant, a beacon. But Rigel is not best understood as a thing sitting there unchanged. It is better understood as a process in motion, a vast unstable compromise that is radiating expanding and bleeding material into its surroundings at the same time. Even the phrase outer layers becomes more revealing once the scale is felt properly. These are not thin decorative skins. They are enormous regions of hot stellar gas extended across a radius so large that the surface gravity is far weaker than intuition expects. That weaker grip matters. It means less force is needed to lift matter away. It means radiation has more leverage. It means that in a star already spending its future, rapidly part of the price of luminosity is literal escape. Matter that might once have remained part of the star instead joins the circumstellar environment, becoming part of the wider medium from which later structures may form. So the wind is not simply waste, it is also transfer. Massive stars do not keep all the material they are born with. They return part of it before they die. But that generosity is not voluntary. It is structural. Rigel gives matter back because it cannot remain fully closed under these conditions. And this introduces another deeper layer. The star is not only consuming fuel in the core, it is also being reduced from the outside. Interior expenditure and exterior loss are happening together. The core burns to maintain the star against gravity. The radiation born from that burning helps strip mass away from the envelope. The same brilliance that makes Rigel famous therefore contributes to the slow dismantling of the object that produces it. This is why the wind matters so much narratively. It is the first place where the star's power becomes visibly double-edged. Rigel is not merely threatened by some future event called collapse. It is already being shaped by its inability to remain wholly intact. And because the star is so luminous, the surrounding space does not remain untouched either. Massive stars ionize nearby gas, sculpt their environment, and pour energy into the regions around them. Their influence extends far beyond their visible surface. They are not isolated lamps. They are active agents inside a wider structure. This is where the frame begins to widen again. What first seemed like the story of one star becomes the story of a star, and its surroundings a system of radiation mass loss and environmental consequence. The answer seems clear until the scale becomes visible. Then even the word wind starts to feel too gentle. What Rigel is doing is not breathing. It is leaking power into matter so effectively that part of the star is continually persuaded to leave. And once that becomes clear, another simplification fails with it. Rigel is often imagined as a single brilliant object standing alone at the foot of Orion, but the deeper truth is more complicated. The star belongs to a richer gravitational and physical context, and the closer one looks, the less adequate the idea of a lone, self-contained beacon becomes. Which means the next layer of the story is not just what Rigel is losing, but what Rigel is embedded in, because once a massive star begins reshaping space around itself, the question is no longer only how the star survives. The question becomes whether Rigel was ever truly alone in the first place. The sky turns systems into symbols. That is one of its oldest tricks, and Rigel is a perfect victim of it. To the unaided eye, the star appears singular, self-contained, a bright point occupying one clean position in Orion, as though all its meaning can be held inside that one sharp light. Human perception likes that version of reality because it is easy to carry. One star, one place, one identity. But the deeper story resists that simplicity. Rigel is not best understood as a lonely beacon suspended in empty darkness. It belongs to a more complicated gravitational setting And that complication matters because it widens the frame again. The obvious explanation is that the star's story begins and ends inside its own body. The real explanation is that even a star as dominant as Rigel does not stand entirely alone. It is part of a multiple star system with fainter companion stars bound into the same larger arrangement, and that fact changes the emotional meaning of what we are seeing. The bright blue supergiant still dominates the system. It still provides almost all of the spectacle. But the spectacle is no longer the whole truth. What seemed like a single object becomes a hierarchy, a structure, a local environment shaped not only by one overwhelming star, but by relationships between stars of very different scale and brightness. This matters for two reasons. First, it exposes how badly the eye can simplify the universe. Second, it reminds us that massive stars are not merely isolated performances of physics. They emerge from broader conditions and often remain embedded in them. This is where the story of Rigel shifts again from object to structure. The star that looked like a solitary declaration in Orion turns out to be part of a family, though one so uneven that the brightest member overwhelms the rest. That imbalance is revealing. A dominant primary star can make companion stars feel almost irrelevant from a distance. Yet their existence proves that the local architecture is richer than the naked eye admits. Astronomy advances every time that kind of simplification breaks. One point of light becomes a binary. A binary becomes a multiple system. A multiple system becomes evidence about stellar birth mass orbital history and the conditions in which stars form. The story on the surface is one shining star. The story underneath is an arrangement of bodies whose visibility is distributed unevenly by power. Rigel's main light drowns the weaker members so completely that for most of human history, it might as well have seemed alone. That is not because the rest were absent. It is because brightness creates authority. The strongest source dictates perception. In the universe, dominance can erase context. A powerful thing can look self-sufficient, when in fact it is merely overwhelming the evidence around it. Rigel teaches that lesson beautifully. The blue supergiant remains the central actor. But once the companions are recognized, the system stops looking like a monument and starts looking like a history. Companion stars imply shared origin, or at least long gravitational entanglement. They imply a past in which this region of space was not just a stage for one star, but a site of formation and survival under more crowded conditions. Massive stars are generally born in star-forming environments, not in philosophical isolation, and the existence of companions helps pull Rigel back into that broader truth. It was never just a light. It was always part of a larger story about how matter collapses fragments and organizes itself into unequal systems. The achievement is real. The loneliness is exaggerated. There is another reason this matters. When a star is imagined as solitary, its future can be narrated too neatly. It lives, it evolves, it dies. But once a system is acknowledged, even if the dominant star remains overwhelmingly the most important component, the frame becomes more complex. Gravity does not disappear outside the main body. Companions orbit. Distances matter. The local environment is no longer empty background. It becomes part of the meaning of the star. Not because the companions rescue Rigel from its fate. They do not. The internal evolution of a massive blue supergiant still governs the main line of the story. But the presence of companions reminds us that stellar life is rarely staged against pure nothingness. Massive stars influence nearby bodies with radiation winds and gravity. They alter the environment in which those bodies exist. And eventually, when the dominant star enters its terminal phases, the system around it may become one of the first witnesses to the consequences. This only looks like a lone jewel from Earth. In physical reality, Rigel occupies a neighborhood, and neighborhoods change the meaning of events. A supernova in a vacuum is one kind of thought. A supernova in a system is another. The difference is not merely visual, it is relational. It forces the story to acknowledge that massive stars do not just possess futures, they impose futures on nearby space. And that in turn sharpens the deeper point. Rigel's companions do not reduce the tragedy of the main star's life. They intensify it by giving it a setting. They make the star feel less like an abstract example and more like a dominant member of a real stellar arrangement, one whose violence will eventually matter locally as well as cosmically. The answer seems clear until the scale becomes visible. Then the clean image of one blue point in Orion starts to break apart. The star is still itself. The light is still overwhelming. But the system is no longer simple. Beneath the easy human symbol lies a more layered reality, unequal stars' gravitational order, shared history, and a local architecture dominated by one short-lived giant, burning faster than everything around it. That wider frame does not replace the story of Rigel's core. It prepares the next descent. Because once the idea of the star as a solitary object has been broken, another simplification must fall with it. Rigel cannot keep living on hydrogen forever. When that easy fuel gives way, the terms of survival change, and the star is forced into harsher burnings in which each victory is shorter, each layer of fusion is less forgiving, and each step brings the final collapse closer. A massive star does not keep winning by doing the same thing forever. That is the next rupture in the story, and it matters because it destroys the most comforting simplification left. So far, Rigel can still be imagined, at least loosely, as a great hydrogen-burning star under terrible pressure, a blue supergiant whose brilliance is the outward expression of one central process carried to extremes. But that picture is only temporarily true. The deeper reality is more violent and more layered. As the core exhausts its easiest fuel, the star is not granted rest, and it is not allowed to remain what it was. Instead, gravity begins reclaiming authority. The core contracts again, temperatures rise further, and new forms of fusion become possible. The obvious explanation is that a star shines until it runs out of fuel. The real explanation is that a massive star is forced through a sequence of increasingly unforgiving burnings, each one harder one, each one shorter-lived, and each one more dangerous than the last. This is where stellar evolution stops looking like steady illumination and starts looking like a staircase of emergencies. Hydrogen fusion is the opening bargain, not the final one. Once hydrogen in the core is exhausted or depleted enough to change the balance, the central pressure support weakens. Gravity does what it has always wanted to do. It squeezes inward harder. That contraction heats the core further, and if the star is massive enough, as Rigel is, the temperature can rise to the point where helium fusion begins. Now the engine has changed. The star is no longer relying on the same central fire that defined its long earlier chapter. It has entered a harsher phase in which new nuclear pathways become possible. New energy flows appear, and the structure of the star must reorganize itself around a different internal reality. The story on the surface is still one brilliant star. The story underneath is a succession of physical regimes, each more costly than the last. This is one of the great hidden truths of massive stars. They do not simply burn. They graduate into more difficult forms of burning under coercion. Each new stage exists because contraction has pushed matter and temperature to another threshold. Each threshold buys time, but less time than the one before. Each success is more temporary. Helium can fuse into heavier elements. Later, under still greater compression and heat, carbon burning can follow. Then neon, then oxygen, then silicon. The exact path depends on mass internal structure and the details of stellar evolution. But the larger logic is the same. The star keeps descending into more extreme chemistry because gravity keeps narrowing its choices. This is why the phrase fusion changes. The terms is not just a poetic line. It is a literal description of how Rigel's future hardens. A smaller star like the Sun never reaches most of these stages. Its core will not be driven to the required temperatures. It lives long partly because its ambitions are limited by mass. Rigel has no such modest path available. Its great mass gives it access to more advanced burning. But that access is not a privilege in any peaceful sense. It is a sentence to deeper instability. The achievement is real. The countdown accelerates, and with each new stage the timescales collapse. Hydrogen burning can define a major chapter of a star's life. Helium burning is shorter. Later stages can become shockingly brief by comparison. The more advanced the fuel, the less time the star can sustain itself on it, because the conditions are so extreme and the energy balance grows less forgiving. This is the deeper insult of stellar greatness. Rigel's interior may begin to look more impressive as it moves into heavier fusion, but the increased sophistication is inseparable from impending failure. The star becomes more internally complex at exactly the moment its remaining future shrinks. Human beings are used to complexity, suggesting maturity, refinement, or progress. In massive stars, complexity often means the endgame has begun, and the structure of the star becomes stranger as a result. The core and the surrounding layers no longer tell one simple story. Instead, the star can develop shell burnings around an evolving center with different layers dominated by different nuclear processes. What looks from afar like one coherent object is inside becoming more like an onion of catastrophes, nested shells of fusion arranged around a core marching toward a dead end. This only looks like one flame from a great distance. In reality, it becomes a hierarchy of fires, each one dependent on the failures beneath it. That is what makes the later life of a massive star so unnerving. It is not merely bright, it is internally crowded with consequences. The old simple identity of the star begins to fracture. Rigel remains Rigel to the eye, but physically it is becoming a more unstable compound of layers, reactions, and narrowing options. And every new stage changes the stakes. Heavier elements accumulate. The core composition shifts again. The star keeps surviving, but survival becomes less like stability and more like a series of increasingly desperate negotiations. This is the point where the meaning of power changes once more. At the beginning, power meant brightness. Then it meant pressure. Then it meant accelerated consumption. Now it means access to burnings so advanced that only the most massive stars can achieve them. And that access is terrible because it leads not to renewal, but to terminal escalation. The answer seems clear until the sequence becomes visible. Then a star is no longer just a source of light. It is a machine being driven through progressively harsher operating modes, each one producing a brief reprieve while preparing a worse crisis underneath. Rigel's future, therefore, is not one continuous blaze. It is a chain of increasingly unstable victories against gravity, and chains like that do not continue forever, because there is a point at which fusion stops offering rescue. There is a point where the star reaches an element that cannot pay the price of support. There is a point where the interior engine ceases to profit from more burning and begins moving toward collapse instead. Which means the next layer of the story is the hardest one yet, because after all these fires and all this power, the fate of a massive star turns on the first fuel that cannot save it at all. After all that power, the star is finally defeated by an element that cannot save it. That is the cruelest turn in Rigel's story, because it means the great machine of stellar fusion does not fail when the star becomes weak, but when it reaches a form of burning that offers no profit. Up to this point, every contraction of the core has purchased a new temporary reprieve. Hydrogen is consumed. Gravity tightens its grip, the core heats further, and a harsher kind of fusion begins. Then that phase ends, contraction returns, and the next threshold is forced open. Again and again, gravity threatens collapse, and fusion buys time. The obvious explanation is that a massive star simply keeps climbing this ladder until it runs out of material altogether. The real explanation is darker. There is a stopping point built into nuclear physics itself. A massive star can fuse lighter elements and gain energy from the process. But once the core is dominated by iron, the bargain breaks. Iron is the dead end. Iron does not provide a new rescue. Iron turns the whole logic of survival against the star. This is why the deepest crisis in a massive star is not merely fuel depletion in the ordinary sense. It is the arrival at a fuel that is no fuel at all. To understand why, it helps to remember what fusion has been doing from the start. In every earlier stage, the core survives because combining lighter nuclei releases energy. That energy becomes pressure. That pressure helps support the star against gravity. The star lives by profiting from nuclear rearrangement, but iron sits near the point where that profit disappears. Fusing iron into heavier elements does not give the star usable net energy the way earlier fusion stages do. Instead of helping hold the structure up, it becomes energetically futile or worse. The achievement is over. The cost remains. That is what makes iron so devastating in the life of a massive star. It is not poisonous in a chemical sense. It is fatal in a structural one. The story on the surface is still a bright supergiant in Orion. The story underneath is a core approaching the first major element that cannot be turned into renewed support. And once that happens, the meaning of everything changes. Up to this point, contraction has been a threat that also creates the conditions for temporary rescue. The core tightens heats and finds a new way to fight back. But once iron dominates the center, contraction no longer opens another stable chapter. It begins opening the trapdoor. This is the point where the entire history of the star turns against itself. All the previous burnings, all the brilliance, all the pressure, all the success in manufacturing heavier elements, all of it has been carrying the core toward a state that cannot continue the old arrangement. The star has been building the instrument of its own failure. That is the hidden irony inside stellar grandeur. Massive stars are celebrated as cosmic forges because they make many of the heavier elements needed for later worlds and later life. But the forging process is inseparable from doom. The more advanced the core becomes, the closer it moves toward an element that ends the profitable era of fusion. Rigel's greatness, therefore, is not just that it can reach these stages at all. Its greatness is tragic, because access to advanced fusion is also access to terminal physics. Human beings often imagine progress as a ladder whose upper rungs promise greater command. In massive stars, the upper rungs lead into a wall. Orion is that wall. It represents the point at which the star's old strategy can no longer work. And once the core can no longer earn enough energy from fusion, gravity is no longer negotiating from a distance. Gravity begins winning directly. This is what makes the Orion core such a terrifying threshold. It is not simply a new composition. It is the moment when the center of the star ceases to be an engine of support and becomes a liability too massive to hold itself up by previous means. The outer layers may still exist in all their grandeur. The radiation may still blaze into space. The star may still appear powerful to any distant observer. But the real problem is no longer the visible star. The real problem is that the core has lost the ability to defend the structure above it. And because the mass of the overlying layers is immense, the failure is not gentle. A massive star cannot just shrug and cool down from this point. The whole architecture of balance depends on central pressure support. Remove that support, and the center begins to collapse with terrifying speed. This is why the accepted surface image of stellar death is too simple. The catastrophe does not begin when the star explodes. It begins when the interior reaches a state where fusion can no longer pay the energy bill required to resist its own weight. The explosion comes later. First comes bankruptcy. First comes the realization that the most powerful stars in the sky are living on a system that only works as long as the core can keep turning nuclear change into outward support. Orion ends that. Orion is where the old currency fails. The answer seems clear until the mechanism is fully visible. Then the fate of a massive star no longer looks like a vague eventual tragedy. It looks like a precise physical trap. Rigel burns through one regime after another, forcing gravity back each time, until at last the center fills with a substance that offers no meaningful new defense. From that moment, the star is no longer negotiating its future through fusion. It is preparing for implosion. And once that threshold is crossed, time itself changes character because the long ages of burning collapse into a far more violent sequence in which the core gives way, the outer star loses the support it has always relied on, and the history of millions of years begins rushing toward a collapse that can unfold in less than a second. The longest story in Rigel's life ends in one of its shortest moments. That is the next reversal, and it is almost impossible to feel properly on first encounter, because the scales are so violently mismatched. For millions of years, the star builds itself through pressure, fusion loss, adaptation, and increasingly desperate internal negotiations. Then the core reaches the point where those negotiations fail, and the decisive collapse does not unfold over ages, centuries, or even days. It unfolds with terrifying speed. The obvious explanation is that a massive star dies because it slowly runs out of fuel and gradually falls apart. The real explanation is that once the iron-dominated core can no longer support itself, the center gives way in a runaway collapse that transforms the entire logic of the star in moments. The long prelude matters immensely, but the trigger when it arrives is brutal. Up to this point, gravity has always been the enemy that also creates the possibility of rescue. It compresses the core, raises temperature, and forces new burning stages into existence. But when fusion can no longer provide meaningful support, gravity stops behaving like a negotiator. It behaves like a verdict. The core begins to fall inward. And because the material at the center is already under such extreme density and pressure, the collapse is not a gentle settling. It is a rapid inward rush in which the structure of matter itself becomes part of the crisis. Electrons are forced into protons, producing neutrons and neutrinos. Pressure conditions become so severe that familiar atomic architecture ceases to matter. What had been the center of a star becomes an imploding region, moving toward one of the most extreme states in the universe. This is the point where ordinary language about burning stars breaks down. Rigel is no longer primarily a star radiating into space. It is becoming a collapsing core, dragging the rest of the star into consequences it cannot escape. And the speed matters because it changes the emotional meaning of stellar life. A star can spend millions of years preparing the terms of its death without revealing how abruptly those terms will finally be enforced. That is one of the deepest shocks in astrophysics. Gradual evolution can lead to sudden failure. The story on the surface is duration. The story underneath is instability waiting for the exact moment when support fails. Human beings know this pattern in other systems. Empires erode for decades and then break in a season. Structures weather slowly and then collapse at once. Massive stars obey a cosmic version of the same logic. Rigel's outward brilliance may appear continuous, but the continuity is deceptive. It depends on a core that must remain in balance. Once that balance is lost, the timeline compresses catastrophically. The center falls inward faster and faster. Densities rise toward extraordinary extremes. Neutrinos are produced in immense numbers. The inner regions approach the point where matter can resist further compression, only through forces far more severe than the thermal pressure that supported the star before. And then comes one of the strangest transitions in nature. The collapsing inner core can stiffen abruptly when nuclear densities are reached, creating a rebound effect against the infalling material above. But even that does not mean the star has been saved. The first bounce is not the final solution. The easy explanation is that the core hits bottom and blasts the star apart. The real explanation is harder. The collapse creates a shock, but that shock must fight its way through a still infalling star, and without additional energy, it can stall. This is why core collapse is not just a dramatic event. It is a battlefield of processes unfolding at extraordinary speed. Infall compression, neutrino production, shock formation, shock loss, and the struggle to turn implosion into explosion. The achievement is real. The rescue is not automatic. That is what makes this stage so different from everything that came before. Earlier in Rigel's life, survival meant sustaining a balance. Now the problem is whether the collapse can be reversed outward, strongly enough to unbind the star's outer layers at all. And much of the violence is hidden from direct view, buried beneath layers that still have not yet learned the center has failed. This is another reason the death of a massive star is so conceptually difficult. The star does not explode because the entire object somehow decides at once to end. The center fails first. The rest of the star is then forced to respond. The catastrophe moves from core to envelope, from microscopic physics to stellar-scale violence, from invisible collapse to visible ruin. This only looks like a bright star in Orion from Earth. Inside, at the crucial moment, it becomes a system in which gravity degeneracy, nuclear stiffness, and neutrino transport decide whether millions of years of structure will be blown apart in one terminal event. The answer seems clear until the scale of the transition becomes visible. Then, the death of a massive star stops looking like a slow extinguishing and starts looking like a trap snapping shut. Rigel does not fade into irrelevance when its core fails. It enters the most compressed and violent stage of its existence, where the central collapse can happen in less than a second, even though the star's life has stretched across millions of years. That contrast is the real shock. The sky teaches people to think of stars as fixed. Physics reveals that fixity can conceal one of the fastest structural failures in nature. And yet, even this is not the whole truth. Core collapse is the turning point, but it is not the full meaning of Rigel's end. The implosion matters because of what it enables next. If conditions align, the trapped violence of the center becomes an outward event of astonishing power. The star's death becomes visible not merely as collapse, but as ejection shock radiance and transformation on a scale large enough to seed the future. Which means the next layer of the story is not the fall inward, but the explosion outward, because the collapse of Rigel's core is only the hidden beginning of the event. Most people think of first the supernova itself, and the question of what that explosion really leaves behind. The explosion is the part humans remember, but it is not the part that does the deciding. That is the next correction Rigel forces on the story. By the time the supernova becomes visible, by the time the star tears open in light and ejecta and shock, the central question has already been answered beneath the surface. The core has failed. Collapse has happened. The old balance is gone. What follows is not the beginning of death, but the conversion of that hidden death into an outward event large enough to rewrite the surrounding space. The obvious explanation is that a massive star explodes because it becomes too violent to contain itself. The real explanation is that the explosion is born from collapse, from the release and redistribution of energy when the core gives way and the rest of the star is forced to respond. This matters because it changes the meaning of the supernova completely. A supernova is not a star simply blowing up like a bomb. It is a structure losing its center and then suffering the consequences at every larger layer above it. The story on the surface is detonation. The story underneath is failure of support. Once the inner core collapses and the shock is launched, the outer regions of the star are suddenly living under new law. For most of Rigel's life, those layers have been held aloft by the pressure generated beneath them. Now the source of that support has been catastrophically altered. If the shock can be revived strongly enough and driven through the overlying star, the outer layers are blasted outward at enormous speed. Energy that had been trapped inside the star's structure is re-expressed as violence on a scale ordinary language barely contains. Light floods outward. Matter is torn free. Elements forged over the star's lifetime and in the explosion itself are hurled into the interstellar medium. What had looked like a stable luminous object becomes a wreck expanding into space. This only looks like one event from a distance. In physical reality, it is a chain core failure, collapse, rebound shock, energy, transfer, ejection, radiation, aftermath. And every link matters. That is why the supernova should not be treated as a dramatic flourish attached to an otherwise separate stellar biography. It is the biography concentrated. It is the final accounting of everything Rigel has been building toward since the day gravity first forced fusion to begin. Every earlier contradiction returns here in harsher form. The star's great mass, once the source of extraordinary power, becomes part of the burden that must be overcome. The star's layered complexity, once a sign of advanced burning, becomes the material the shock must traverse. The star's production of heavy elements, once hidden in the interior, becomes part of what is now delivered outward into the galaxy. The achievement is real. The destruction is how the achievement becomes available to anything beyond the star itself. That is the first larger meaning of supernovae. They are not only endings, they are distribution events. They take what was locked inside one massive star and scatter it into space, where later stars, planets, atmospheres, rocks, and bodies may one day inherit it. Human beings tend to think of death as subtraction. In massive stars, death is also transfer. Not merciful transfer, not gentle transfer, violent transfer. Rigel does not leave the stage quietly. If it dies as a core collapse supernova, it will throw part of itself outward with enough energy to outshine entire galaxies for a brief period. That brightness, too, must be read correctly. It is not simply one last display of strength. It is the visible consequence of structural ruin. The star becomes most spectacular at the moment it stops being a star in the old sense at all, and that may be the harshest irony yet. Rigel's brightest chapter as an event may arrive only when its identity has already been broken beyond repair. This is why massive stellar death feels so disproportionate. A star spends millions of years building itself, and only a tiny fraction of that time unbuilding itself. But the unbuilding is what the wider universe can often see most clearly. The explosion writes the hidden truth across interstellar distances. It announces that something which seemed fixed was temporary, that something which seemed singular was actually a source of future material, and that the sky's apparent stability is built partly on events so violent they can reset whole local environments. The supernova does not merely mark the end of Rigel's old structure. It sends a shock through surrounding gas stirs nearby. Matter enriches the region with heavier elements and changes the physical conditions under which later stars may form. So even in destruction, Rigel remains causally powerful. It ceases to be what it was, but it does not cease to matter. This reframes the whole star one more time. Rigel is not merely a beautiful light destined for ruin. It is a temporary concentration of matter whose final disruption helps create the ingredients and conditions for other structures elsewhere. The answer seems clear until the aftermath becomes visible. Then the supernova is no longer just a brilliant ending. It becomes a handoff between generations of matter. What dies as a star may continue as debris, enrichment, pressure, radiation, and inheritance. And yet, even this broader meaning leaves one hard question unresolved. When the outer layers are blasted away, not everything escapes. The center, the place where the star's entire fate has been decided from the beginning, remains behind in altered form. The explosion can scatter the envelope, but it does not erase the collapsed remnant. Something survives the blast. Something compact, dense, and extreme is left at the site of failure. Which means the next layer of the story is not the ejected star, but the surviving core, because after all the grandeur, all the burning, and all the violence, Rigel's final identity may depend less on the explosion people see than on the remnant the explosion cannot destroy. What survives? Rigel may be smaller than a city or darker than a horizon, and that uncertainty is part of the truth, not a flaw in it. After all the blazing surface, all the swollen scale, all the radiation, all the mass loss, all the advanced fusion, and all the violence of collapse, the final question narrows to the remnant. What is left when the outer star is torn away and the core is forced into its last defensible shape? The obvious explanation is that a massive star explodes and leaves behind one standard kind of corpse. The real explanation is harsher and more interesting. Massive stars can end as neutron stars or black holes, and the difference depends not just on how the star was born, but on how much mass it loses, how the collapse unfolds, and how much of the core remains after the explosion has done its work. NASA's overview of stellar deaths notes that the collapsed core of a massive star can survive as either a neutron star or a black hole. While its black hole guide adds that stars near the threshold can leave neutron stars, but stars around 20 solar masses or more can collapse into stellar mass black holes. That is where Rigel becomes especially revealing. Rigel is massive enough to live under the logic of catastrophic stellar death, but it sits near a region where outcomes are not always reducible to a single easy answer. The star begins life with enormous mass, yet it is also losing mass through stellar winds, and those losses matter because the remnant is decided not by reputation, not by apparent brightness in Orion, but by what remains in the core when the structure finally fails. This is the last reversal in the long chain of reversals. What matters most at the end may be the part of the star no one ever sees directly. If the remaining collapsed core stays below the upper limit for neutron star support, then the result is one of the strangest objects in the universe, a neutron star. A body with roughly stellar mass packed into something city-sized matter, compressed so fiercely that the old architecture of atoms no longer survives in recognizable form. NASA describes neutron stars as the remnants of exploded massive stars that were not quite massive enough to continue on into black holes, while other NASA educational material notes that remnants in the rough range of about 1.4 to 3 solar masses can remain neutron stars. If that happens, Rigel's final identity would be a compact monument to resistance, a core that did not escape collapse, but did manage to stop short of vanishing behind an event horizon. Yet, if the remnant remains too massive, if gravity keeps the advantage after the explosion, if the compressed core exceeds what neutron pressure can support, then the collapse continues and a black hole is born. NASA's Hubble explainer says the core can stabilize as a neutron star or further collapse into a black hole if the remaining mass is more than 3 times the Sun's, which turns the end of the star into a deeper kind of disappearance. This is what makes Rigel's future so powerful narratively. The star is not simply heading toward death, it is heading toward a branching point at which matter itself decides whether it can still resist. That branching point gathers the entire biography of the star into one unresolved pressure. How much mass is really left after the winds? How much falls back after the explosion? How efficiently the supernova ejects the outer layers? How much of the center is forced beyond every remaining form of support? The answer seems clear only when the object is kept at a distance. Up close, the ending is more conditional, more physical, and more severe. Rigel may be famous as a bright star, but brightness does not settle the remnant. Mass alone does not settle it cleanly either. The outcome depends on the inner bookkeeping of stellar ruin. This only looks like a single destiny from Earth. In physical reality, the end of a massive star is a contest between what the explosion can throw off and what gravity can hold on to. If the explosion wins enough, a neutron star survives. If gravity retains too much, a black hole closes over the center. That is why the remnant matters so much philosophically as well as physically. A neutron star is collapse interrupted. A black hole is collapse carried beyond visibility. One leaves behind a compact object that can still announce itself through radiation rotation and magnetic violence. The other leaves behind a boundary beyond which the old star cannot be directly recovered. In both cases, the old Rigel is gone. But the manner of its disappearance changes the meaning of the event. The achievement is real. The vanishing is different. And because Rigel sits in the mass range, where that difference feels especially sharp, the star becomes less a simple example and more a reminder that nature does not always give clean endings even when the physics is lawful. Sometimes the deeper truth is that the law itself contains thresholds, and thresholds create suspense. That suspense is not dramatic invention. It is built into the structure of massive stellar death. One future leaves an ultra-dense remnant, still made of matter we can at least in principle study. The other leaves a black hole, a remnant defined by the fact that the matter we most want to inspect has fallen beyond direct view. Either way, Rigel's visible glory collapses into something far smaller and far more extreme than the winter sky suggests. And that is the final wound the star inflicts on intuition. The brightest object in Orion may end not as a grander light, but as a tiny remnant or a darkness with mass. Which means the last section cannot merely describe what happens next. It has to answer what all of this means. Because once Rigel has been reduced from familiar beacon to unstable furnace, from giant star to collapsing core, from explosion to remnant, the larger question is no longer what kind of corpse massive stars leave behind. The larger question is what their brief, violent lives reveal about the universe itself, and why something so destructive is also one of the conditions that makes later worlds possible at all. Rigel matters because the universe builds futures out of violence it cannot avoid. That is the final synthesis, and it is harsher than the beautiful star in Orion ever suggests. For most of human history, Rigel has functioned as orientation, a bright fixed point, the blue-white foot of a familiar hunter, a reliable winter presence that seems to belong to pattern more than process. But the deeper truth is the opposite. Rigel is not important because it helps human beings find Orion. It is important because it reveals what massive stars really are, temporary concentrations of matter forced into brilliance by gravity, driven through extravagant lives, and ended by physics that turns their very success into catastrophe. NASA describes Rigel as a blue supergiant in Orion, with roughly 18 to 20 times the Sun's mass, and notes that high-mass stars live only millions of years. That combination is the whole story in miniature. Great mass, great light, little time. What appears dominant in the sky is, in stellar terms, one of the least sustainable ways matter can arrange itself. The obvious explanation is that the universe produces such stars as masterpieces of abundance. The real explanation is that it produces them as unstable engines objects that can only exist by spending enormous internal order at astonishing speed. Rigel shines because its core has been compressed into ferocious work. It grows vast because its structure must keep adjusting to the demands of that work. It loses mass because its own radiation helps pry material away. It advances into deeper and deeper fusion because gravity keeps tightening the terms. And if it follows the path massive stars are built to follow, it will eventually reach the stage where no further profitable burning remains collapse at the center, and either leave behind a neutron star or continue downward into a black hole. This is the final wound Rigel inflicts on intuition. Human beings are trained by ordinary experience to associate brilliance with triumph size, with security, and visibility with permanence. Rigel overturns all three. Its brilliance is strain made visible. Its size is a costly adjustment, not a guarantee of safety. Its visibility is a trick of distance that hides how brief and contingent its life really is. The story on the surface is one star. The story underneath is a law of the cosmos. Matter under enough gravity does not become calm. It becomes efficient, then extravagant, then unstable, then transformative through ruin. That is why Rigel is larger than its own biography. It is not just a case. It is an example of a universal pattern in which the most spectacular stellar lives are also among the least forgiving. Yet the final meaning is not simply destruction. That would still be too shallow. Massive stars matter not because they die dramatically, but because their short, violent lives alter the chemical and physical future of everything around them. NASA's massive stars engines of creation explains that massive stars fuse heavier and heavier elements, and then spread those elements through space when they explode as supernovas, while other NASA material notes that supernovas seed surrounding gas and dust with heavy elements that later help form new stars, planets, and star systems. That is the deepest reframing of all. Rigel is not merely a doomed light. It is part of the mechanism by which the universe stops being chemically simple. A massive star takes hydrogen and helium, subjects them to terrible pressure, forges heavier elements through successive burnings, and then through collapse and explosion returns part of that history to space. The violence is not incidental. The violence is the delivery system. Without generations of such stars, later worlds would be poorer in structure, poorer in chemistry, poorer in possibility. The calcium in bones, the iron in blood, the silicates in rocks, the oxygen in atmospheres, the dust from which planets gather, these belong to a universe that has been processed through earlier stars and their deaths. This means Rigel's final significance is not that it will one day vanish. It is that even its vanishing would remain causally alive. The star may leave a compact remnant. It may blast material into the surrounding medium. It may help compress nearby gas. It may enrich future stellar nurseries. It may disappear as a familiar point in Orion while continuing as inheritance informs the eye cannot trace back to it. That is what transforms the opening image of the script. The winter sky seems to offer a picture of stability, a clean arrangement of stars that belong to one serene design. But serenity is what great distance does to violence. Orion is not a static emblem. It is a temporary projection of objects living under very different clocks, carrying very different risks, and moving toward very different endings. Rigel, one of the brightest members of that constellation, is not a permanent jewel pinned to the heavens. It is a brief blue supergiant, burning through a costly life, a star whose beauty is inseparable from instability, and whose death, whenever it comes, will not merely close a story, but redistribute it. The answer in the end is larger than Rigel itself. Massive stars are the universe, showing that creation is often front-loaded with pressure, that splendor can be a countdown, and that endings are sometimes the only way matter reaches its next beginning. Rigel shines over Orion now as if it were a finished thing. It is not finished. It is in transit, and that is why it matters. Rigel does not ask to be admired for long. It asks to be understood correctly. Not as a permanent jewel in Orion, not as a symbol of calm winter geometry, but as a star living under one of the most expensive arrangements the universe can produce. Everything that makes it magnificent also makes it temporary. Its mass forces the pressure. The pressure drives the fusion. The fusion creates the light. The light helps strip the star away. And when the deeper burnings run out of room to save it, gravity takes back the argument in full. That is the whole pattern. Brilliance is not the opposite of fragility here. Brilliance is the evidence of it. And yet, the story does not end in simple loss. That would still be too small. A star like Rigel lives fast, dies violently, and leaves behind more than a remnant. It leaves structure. It leaves altered space. It leaves heavy elements, shock inheritance, and the raw conditions from which later worlds may gather. The universe does not build complexity gently. It builds it through pressure, instability, collapse, and redistribution. Massive stars are part of that terrible generosity. They do not merely light the dark, they change what the dark can later contain. So the next time Orion rises, Rigel can still be what it has always been to the eye, a brilliant fixed point, clean and distant and sure. But now the image carries a deeper truth. That blue light is not the sign of permanence. It is the sign of a star spending itself at extraordinary speed. It is the visible edge of a larger hidden process, one in which beauty and violence are not separate stories, but the same story seen from different distances.